Hello, welcome to the fifth lesson of our fourth unit, Acute Angle Trigonometry, for our grade 11 University College math class. So, the second half, this is the first lesson of the second half of the Acute Angle Trigonometry unit. So what we've been working with up until now has been right angle triangles exclusively. And there are three tools that we had in our tool belt that we could use with right angle triangles to find sides and angles. The first, the sum of interior angles. So if you have two of the three interior angles, you can find the third by subtracting the first two from 180. Second tool is the Pythagorean theorem. And the Pythagorean theorem we use if we have a right angle triangle and have two sides, we can find this third using the Pythagorean theorem. And the last one is primary trig ratios, where using particular configurations of side lengths from a reference angle, we can find angles of reference and we can find side lengths in a right angle triangle. So, what if we don't have a right angle triangle? That's what the second half of this unit is going to be about. If we don't have right angle triangles, all of a sudden, and I'm just going to do a little drawing here, you don't have to copy this down, I'm just going to pop it in here. So if we have a right angle triangle, this is kind of what it looks like. If we don't have a right angle triangle, the thing that we lose is access to a hypotenuse. Hypotenuse only occurs, it's a special side, it only occurs in right angle triangles. And without right angle triangles, all of a sudden you don't have a hypotenuse anymore, which means that we're going to lose two of our, that's a highlighter, we're going to lose two of the tools that we've been previously using. We don't have Pythagorean theorem, Pythagoras, don't have that one anymore, and we don't have the primary trig ratios because all of those use hypotenuse in them in some way. So because we don't have a hypotenuse, we don't get to use Pythagoras anymore, we don't get to use primary trig ratios, so we're down to kind of one tool in our tool belt, and that's the sum of interior angles, because that kind of works for any triangle, which is nice. We are, however, two tools down. We need to develop some more tools to find angles and sides in non-right angle triangles, which leads us to today, the sine law. So the sine law is a tool that we use to find either sides or angles. It's over here, listed in this sort of box right here. I would say you don't really have to memorize both of them, since the bottom one is sort of just an inversion of the top one. All you really need to remember is that top piece right there. And really what it means, if you're looking for a sort of an explanation as to how the sine law works, it really is an extension of the proportionality of triangles, which means that the sine of angle A and the side across from it, side little a, proportionally those two values will be equal to the sine of angle B over side little b, or the sine of angle C over side little c. So it's a sort of a fancy way of saying all of these side angle combinations in a triangle are going to be proportional to each other. And that makes sense, right? If you can imagine, the largest angle in a triangle will be across from the largest side. And by extension, the smallest angle in a triangle will be across from the smallest side. So this makes sense to us in our brains. This is a tool that we can then apply to find missing angles and missing sides in non-right angle triangles. So the part I want to focus on is right here at the bottom. So basically we can use, I'm reading this part right here, basically we can use the sine law when we have a corresponding side angle pair plus one other piece of information about the triangle. So I've made sort of a mess of this little triangle here, circling the sides that are across from each other. Really what it's saying is, if you have angle A and side A and any one other piece of information, you can use the sine law. You need to have one completed ratio from up here, whether it's sine A over A, sine B over B, or sine C over C. One completed ratio and then one more piece of information will allow you to use the sine law to find missing pieces of information in non-right angle triangles. So let's do an example here. Zoom back out, head to the second page. So here is our first example. Now I'm going to leave this up here. This is the way that I normally set up a question like this. You'll notice that triangle PQR, as I've drawn it, isn't necessarily accurate in that I don't know that angle Q is 69 degrees or angle R is 68 degrees. I didn't draw them with a protractor or anything like that to make sure that they're perfect. I'm just drawing a triangle for reference so I can visually see what information I have and by extension which tools I can use to find missing pieces of information. So I do want to point out right off the bat, we're being asked to solve triangle PQR, which means find all of the missing pieces of information. We've been given 3. What we've been given, I'll zoom in just a little bit more, and I'm going to kind of hold it here. If you need a moment, now's a good time to pause and then sort of copy this piece down, since this is the framework that I'll be using as we go forward solving any triangles, but today in non-right angle triangles. So I've drawn not only the triangle with the pieces of information put in it, I've also made this little table thingy right down here. This is a way of just keeping track of the things that we know and the things that we don't. Once you've got this copied, I want us first to look and ask ourselves, is this a right angle triangle? And it isn't. We know this because we've already got 68 degrees and 69 degrees taken care of in our right angle triangle. There's going to be no 90 degrees in this triangle, so for us that means it's not a 90, which means that we're not going to be using Pythagorean theorem and we're not going to be using primary trig ratios. We need to use something else. Obviously today, the goal is to get practice using the sine law. So we're going to start there. What's unique about this particular setup is we've been given 2 angles and a side, but we don't have any side angle pairs that have been given to us. However, what we do know about any old triangle is that we can use the sum of interior angles to find a third angle given 2 others. So number 1 is going to be to find angle P. Because we've been given 2, and we know that the total is going to be 180, we can subtract those 2 values. Oh, should put some degrees on that thing. If we subtract the 2 values we've been given from 180 degrees, we can find out what angle P is equal to. So 180 minus 69 minus 68 is going to give us 43 degrees for angle P. And I'm going to put that into my table. 43 degrees. And I guess I can put that in the old triangle here too. 43 degrees. So this was a pretty straightforward calculation. Nothing sort of fancy happening here. But I will say that by doing this first step, what we have now is a side angle pair. So visually that's what it looks like up here, where we have the angle and the side across from it. So we have a side angle pair, and we have not only 1 but 2 more pieces of information. If we're looking at it visually in the table, it's having 1 piece of information and then another piece of information across from it. So by finding 43 degrees, we now have a side angle pair, and it allows us to use sine law, in this case, to find angle or side length little q and side length little r. Now it doesn't really matter which one we find first, so I'm just going to pick alphabetically to find little q first. So let's find side little q. So we're going to set up a sine law here. Now I'm going to use the letters that were provided for us in this triangle. So we have the sine of r over r equals the sine of q over q. My next step is going to be to substitute. Oh, sorry, that shouldn't be r. Those should be p's. My apologies. Let's fix that before we get too far in here. Sorry, sine of p over little p equals sine of q over little q. Much better. And now we're going to substitute. So the sine of 43 degrees over side little p, which is 21, will equal the sine of 69 degrees over side little q. That's our unknown. Now, what I've been saying throughout this whole unit is that sine 43 degrees is a number. Sine 69 degrees is a number. We don't want to calculate those just yet, because when we type that into our calculator, so if you have a calculator nearby, we can just type in the sine of 43 degrees, hit equals, and that's 0.681998836, etc. It goes on. We don't want to round that until we have to. So I'm going to suggest that we isolate side little q by using algebra first and doing all the calculations right at the end. So if I cross multiply here, I've got side little q times sine of 43 degrees equals 21 times sine of 69 degrees. Now to isolate side little q, I'm going to divide both sides by sine of 43 degrees, because again that's a number, sine of 43 degrees. And now I have side little q being equal to approximately, now I'm going to type this whole mess into my calculator right now. So I type in 21 times the sine of 69 degrees equals, divided by the sine of 43 degrees, and that's going to equal 28.7. So we have 28.7, and I don't know if we were given units here. We were. Those will be centimeters. So we have 28.7 centimeters approximately for side little q. And let's put that in. 28.7 approximately. And now we have one more side to find. We are going to find side little r. So I'm going to set this up in exactly the same way. Number 3, find side little r. I'm going to set this up as sine of p over p equals sine of r over r. And I'm going to do some substituting. So sine of 43 degrees over 21, I think it was, equals the sine of 68 degrees over little r. Now some people might be wondering, why did I use sine p over p again? Could I use sine q over q? The answer is, in theory, yes, you could use sine q over q. However, what if you made a mistake over here in finding the length of side little q? You would be further compounding your mistakes if you use values in subsequent calculations that you were responsible for finding. It doesn't necessarily mean you made a mistake, but it's always safer, so rule of thumb, it's always safer to use values you've been given in the question when you work through a multi-step problem. Now in this case it's true we had to find 43 degrees on our own, but that's a pretty straightforward calculation and there wasn't any rounding that was done there. So in theory that should work out just fine. Okay, so let's finish this guy up. Again, our variables down here. We want to do the algebra before we start doing calculations. So we have r times sine of 43 degrees equals 21 times sine of 68 degrees. To isolate our side little r, we're going to divide both sides by sine 43 degrees. And now we're going to type this whole mess into our calculator. So let's get a gander at this. We type in 21 times the sine of 68 degrees equals, divided by the sine of 43 degrees, and that equals 28.5 centimeters approximately. So I'm going to put that into my table, 28.5. Now the last thing I want to do when working through a question like this is take a look at the answers that I have found, and I want to perform what's called a dummy check. So what I want to do is make sure, I'm just going to erase the highlighter there, I want to make sure that I haven't just relied completely on my calculator and disconnected my brain from reality. We know that the largest side should be across from the largest angle. So the largest side that I have is 28.7, and is it across from my largest angle? It is. And now if I want to find my smallest side, that was side 21, is that across from my smallest angle? It is. So this is what I call a dummy check. It just makes sure that you don't mindlessly type stuff into your calculator and take whatever it gives you, because calculator errors are a real thing. So I'm going to stop the video here, and then we'll move on to the second example in the second part of this video. So hang tight.